let us start here. So it says 4.4, conservation of energy for a control volume. So the last section we did was conservation of mass. Conservation of mass is exactly what it sounds like, right? Essentially, we are conserving mass, and mass entering the system has to be mass leaving the system, right? Because we didn't lose it somewhere along the way. It is still in the system somewhere. And so now we're going to do an energy balance for a controls volume. So in the previous exam and previous chapter 3, we did energy balances for a closed system, right? We did energy balance for that. This one is an energy balance for a control volume where mass is allowed to flow through the boundary layer. So we now have to add time to it, essentially. Time is now what we have added to the equation. So let's go ahead and start reading. So it says, we begin by noting that the control volume form of the energy balance can be derived by an approach closely paralleling that considered in the box of section 411, where the control volume mass rate balance is obtained by transforming the closed system form. So essentially it's saying is that we are transforming the original one, so, Q minus W is equal to the delta, the change in energy, right? That equation that we have worked with before. So I'll just write that out if I can. Q minus W, so the heat transfer minus the work has to be equal to the essentially change of energy, right? But the change of energy, if you guys remember, breaks down into kinetic potential and internal energy, right? It's the exact same for this chapter as well. Except that in this chapter, because we have a control volume, control volumes actually have more, and more often, so not in many cases do you have to deal with potential and kinetic energy, but there are times when it is added. So there are times when you do have to do it, and in control volumes, you'll see it more often than the other ones, closed systems. So remember, inside of this delta E is the change of energy of internal energy, the change of energy of potential energy, and kinetic energy, right? And we'll show that equation in just a second, the full one. So let's read this part. It says the present development proceeds less formally by arguing that, like mass, energy is an extensive property, so it too can be transferred into or out of a control volume as a result of mass crossing the boundary. Since it is the principal difference between a closed system and a control volume, the control volume energy rate balance can be obtained by modifying the closed system energy rate balance to account for energy transfers. Accordingly, the conservation of energy principle applied to a control volume states this. This is in words. The time rate of change of the energy contained within the control volume at time t has to be equal to the net rate at which energy is being transferred in by heat at any time t minus the net rate at which energy is transferred out by work at time t plus the net rate of energy transferred into the control volume occupying mass flow. And so right here, this is what it ends up coming down to. This is the equation in actual variable forms, okay? So we have the change in the energy of the control volume with time is equal to Q dot, because remember dot means we have a mass flow rate, there is time involved, so Q dot minus W dot plus mass flow rate of the inlet times the internal energy of the inlet plus the velocity over 2 of the inlet plus the potential energy of the inlet. So really fast, just to make sure everybody's aware, this right here is the internal energy, so int E, right? This right here represents the kinetic energy. And the last one is potential. So this right here is each part of that internal energy, kinetic, and potential that I mentioned earlier. It is velocity, and then gz. So g is gravity, and z is height. This is the height of the inlet. Now, and then you have to subtract, remember, to find the total change in energy of the control volume, we have to subtract off what it is like at the exit. So this is the same thing. It's minus mass flow rate of the exit plus the energy of the exit plus the velocity of the exit plus the gravity times the height of the exit. So this is the very large format. Now, our questions tend to be a little more easy because mass flow rate, we tend to say, oh, it's steady state, right? And if it's steady state, that means that mass flow of the inlet means mass flow of the outlet, and then you can combine these two things. But we'll work on that in just a minute. Just hold on to that for now, what we have here. All right, so right here, let me go ahead and get this out of the way. So it says, the underlying terms account for the rate transfer of internal, kinetic, and potential energy of the entering and exiting stream. So that is these things right here. If there is no mass flow in or out, the respective mass flow rates vanish and the underlying terms drop out. The equation then reduces to the rate form energy balance for closed systems. So essentially, what it has said is that if there is no mass flowing, this is essentially just an internal energy. This is a closed system question, because remember, the change in internal energy, or the change in energy, will then be equal to Q minus W. This stuff will all be gone. So if you get rid of the mass flow rates, it goes back to being a closed system where there is no mass flow rate, right? So it makes sense. Then it says, next, we'll place equation 4.9 in an alternative form that is more convenient for subsequent applications. This will be accomplished primarily by recasting the work term W dot, which represents the net rate of energy transferred by work across all portions of the boundary of the control volume. So let's talk about that in just a second. So it says, because work is always done on or by a control volume where the matter flows across the boundary, it is convenient to separate the work term W dot of equation 4.9 into two contributions. One contribution is the work associated with the fluid pressure as mass is introduced at the inlets and removed at the outlets. The other contribution, noted by work CV, includes all other work effects, such as those associated with rotating shafts, displacement, the boundary, electrical things, right? So essentially, inside of the work term, there are two things, and we are going to talk about those, like how we break that down in just a second. So it says, consider the work at an exit, E, associated with the pressure of the flowing matter. Recall from equation 2.13 that the rate of energy transferred by work can be expressed as the product of a force and velocity at the point of application of the force. Accordingly, the rate at which work done at the exit by the normal force due to the pressure is the product of the normal force, PE, so this is PA, so PE, AE, and the fluid velocity VE. So right here, the time rate of energy transferred by work from the control volume at exit E is this right here, okay? Where PE is the pressure, A is the area, and V is velocity. So then it says a similar expression can be written for the rate of energy transferred by work into the control volume at inlet I. With these considerations, the work term W dot of the energy rate can be written as this. So work dot is equal to work CV plus the work done by the fluid at the exit and at the inlet. So this right here, all good so far. But this is going to reduce to something way easier that you guys will be appreciative of, I hope. So it says, where in accordance with the sign convention for the work, the term at the inlet has a negative sign because energy is transferred into the control volume there. A positive sign precedes the work term at the exit because the energy is transferred out of the control volume there. With AV equal MV from equation 4.4b, the above expression for work can be written as this. So AV, if you guys remember, we've talked about this. This mass flow rate is equal to AV over specific volume. So if you essentially make that substitution here, you will get work CV plus ME times PEV minus MI PI VI. So they just made a little substitution here. And this is going to change in just a second to something way better. So it says, where MI and ME are the mass flow rates and VI and VE are the specific volumes at the exit and inlet. Equation 4.12, the terms MI PI VI and ME PE VE account for the work associated with the pressure at the inlet and the exit respectively. They are commonly referred to as flow work. The term WCV accounts for all other energy transfers by work across the boundary. So, just as a little bit of a recap and to break it down, this part is like a shaft, a piston, electrical, something like this. This is something being input in like a mechanical form, right? There's some sort of shaft going on, there's something. The other part here is generally referred to as, they call it flow work, but this right here is the work of the fluid. So it's work of the fluid. Just to distinguish those two. One of them is a shaft, the other one is just essentially pressure differences and volume differences from the inlet to the outlet. Okay? Now, this right here is about to reduce to something that's extremely helpful to us. And I've mentioned it previously in like other chapters, but today we'll go over it again. So, where do we go from there? So right here, we go to one-dimensional flow form of the control volume energy rate balance, okay? So we've already seen this equation right here, right? Except that now we have this added. We have that PI, VI, and PEVE added to the question, right? Or the equation. So what that accounts for is that this is the mass flow rate times the internal energy. So this right here is internal energy. This right here is the flow work. This right here, kinetic energy, and the last one is potential energy, right? Same as the other one over here. And so, we have now changed the equation just a little bit, but this is where it all comes into play right here. So right here, the last two terms of equation 413 can be rewritten using the specific enthalpy H introduced in section 3.61, with, if you guys recall, H was equal to U plus PV, right? And I mentioned it back then that enthalpy is used in open systems and closed systems is internal energy. So this is now an open system, and the reason why we can use it and simplify this is because H is equal to so remember, so let's go ahead and I'll write this out. So how this is going to break down is this is H is going to be equal to M U plus PV, right? So if anyone looks at this equation, what do we have here? No, not this one, the previous one. What do we have here? We have MI UI and MI PI VI. We have this exact setup in terms of these inside of the question, which means that we can remove the UI and the PI VI, and we can replace enthalpy into there. And you guys probably remember that enthalpy is in the tables, right? So that is what we can do. We can now, instead of getting internal energy for questions like this, we get enthalpy, okay? So enthalpy, open systems, control volumes. Internal energy is used for closed systems, like the ones we did in the previous chapter, okay? So, now that we can do that, let's see what the equation turns into. So right here, we have the change in energy of the control volume with respect to time is equal to QCV minus work CV plus MI HI. So this is once again still kinetic potential. And this right here is the work of the fluid, essentially, right? It's the energy and the work of the fluid. Because if you remember, H is equal to that, the internal energy of the fluid plus the work of the fluid. So this term right here, H, essentially encompasses all the things we want to know, right, about this, and it reduces the equation in a very interesting way. And the reason why this enthalpy was created was because of this. You remember when I told you about enthalpy? I said that whenever they were doing their analysis on thermodynamics, they found that this quantity showed up a lot, that U plus PV showed up all the time, and so they were like, I don't want to keep having to write U plus PV and calculating that. So let's just make it a new thing, call it H for enthalpy. So this is something that showed up too much, and they eventually just created a whole table intro for it. So does everybody understand that so far? How that worked, how we made that switch? Okay, I have no questions, so we will move on. So it says the appearance of the sum U plus PV in the control volume energy equation is the principal reason for introducing enthalpy. By the way, I didn't read that previously. It is brought in solely as a convenience. The algebraic form of the energy rate balance is simplified by the use of enthalpy, and as we have seen, enthalpy is normally tabulated along with other properties. In practice, there may be several locations on the boundary through which mass enters or exit. This can be accounted for by entropy summations as a result. So, if there are more than one entrance and exit, you guys probably know that you use the summation sign, and you would sum all entrances, and you'd also sum all exits, right? So for the question we did last time in this class, there would be two entrances, so you would do mi, although so it would be mass flow rate of one entrance times h of the entrance times v of the entrance times this or gz of the entrance. Then you do it again for the other entrance, and then you would finally subtract off the exit one, because there were two entrances, one exit. All right. So it says, in equation 4.15, the one-dimensional flow model is assumed where mass enters and exits the control volume. And equation 4.15 is an accounting balance for the energy of the control volume. It states that the rate of energy increase or decrease within the control volume equals the difference between the rates of energy transfer in and out of across the boundary. The mechanisms of energy transfer are heat and work as for closed systems, and the energy that accompanies the mass entering and exiting. All right. We're not going to go over the integral form because I think the integral form just confuses the hell out of people. So there's no reason to do this. What you guys need to know is this right here. And if there's only one entrance, one exit, then this reduces, right? There's no need for summations. But you guys understand that this right here is the main part of the equation that we need. So we are no longer using internal energy. We'll make that clear. We now have H here. All right. So we're going to pick a question now. We're going to do another question really fast. I'm going to go find one. Although I don't, for some reason, they don't. I'm trying to figure out some of the things that, yeah, okay, so they do talk about it later, but it's really weird because they don't, it says on his notes that it's 4.33 shows the parts that I want to show, but it's not here. So I'm really confused as to that. But really fast, I guess I can go ahead and draw some of these things. So I'll open up a paint and we'll start a question, and but first I'll draw some of these. So some of the things that we're going to see in this class, right, as we move along, some what they're called is like these mechanisms, right, or these processes, I guess is a better way. So these processes. So for the first one we are going to have, so I'll just draw it up here. Oh man, big letters. So the first one up here is a turbine, right? So the first one is a turbine. A turbine in this class generally looks like, although this is going to be bad. You guys will probably make fun of me for my bad. Let's just use the spleen tool. Nope, that didn't work how I wanted it. Never mind. So let's do this. So they generally look like, whoa, okay, they don't look like that. Yeah, they generally look like this. So this right here is a turbine, and so if you see this ever on like a schematic or a process that I have in the homework, this is what a turbine is. And it will tell you that it's a turbine, but this is a turbine. The compressor is the inverse of this, so it's with this part facing over here. So it's just the flip of that. And now then there's a couple other ones that we need to talk about as well. So then we have diffusers and nozzles. So I will draw that one as well. These are ones you'll see more often. So let's do nozzle. So you guys probably know what a nozzle is, I would assume. You'd hope. So a nozzle generally looks like this in our class. Right? And so right here, we would have state 1 and state 2, right? So before the nozzle, it is out here, because obviously I think you guys know what a nozzle does. If you don't know, if you don't know what a nozzle, I just saw what you wrote. So if you want to see a nozzle, this is what it looks like. And so the first stage, nozzles, like I said, all they do is they increase the velocity on the exit, right? That's their goal. Their goal is it's what you put on your hose. It's what is used in jets for like how you fly. Jet engines have nozzles because it's just air difference on either side is how you, or the speed difference is how you move, create thrust. So this right here is a nozzle in our class. The diffuser is the inverse of this. So that means it starts really small and then gets really big at the end. So I can draw that as well, but I think you guys probably can use your imagination here. And it's a diffuser. I hope I spelled that right. Somebody fact check me. So then we have the diffuser, which starts off small. And then branches out. I don't know why it keeps doing that. Yeah, that is aggravating, but that's okay. It's Wednesday, guys, and we're crushing it. So, this right here would be state 1, and this would be state 2 for a diffuser. And so, there are differences we have here, right, in how these things operate. So I'll make the compressor one over here just so we can show basically all of them. I'm pretty sure that's all the ones that you guys will run into. So let's do compressor. Now, okay, before I say that, there is other ones like heat transfer ones, like the ones that remember the one we just did the other day where it's like 2 fluids enter, 1 fluid leave. It's Thunderdome essentially, right? It's that one. That one is there as well, but it's just a heat transfer process, so it's not so much like, it's not so much different than other things that you've seen. So let me go ahead and one. All right, and so the compressor, like I said, is the inverse of this one, so it would be short side over here. Although, once again, you can always tell what one it is just by what way the work is. So if the work is in or out, you can always tell. But this is how I've always seen them, and this is how I've always drawn them. So I'll just keep passing down the knowledge, probably doing it wrong. So this right here is compressor and turbine. So what I was going to show you is that there are different things associated with these. So when we write this equation out, right? So let's write the equation out. If you guys remember, so it is Q, I'm just going to say dot here. So Q dot minus W, or it's QCV, okay. You guys can just call it Q and W. Like, you don't have to write CV as long as you know it's a control volume. As long as you put a dot above it. Put a dot above it. That's all I care about, really. Okay? So Q minus W is equal to M1. Let's just say, so for this one, guys, you guys can clearly see that there is 1 inlet and 1 outlet, right? Is that easy to tell? For these two, at least. Let's look at the nozzle and diffuser. There's 1 inlet, 1 outlet. So that means it would be MI times HI plus V. We're looking at the nozzle, by the way. But these are very similar anyway. V1 squared over 2 plus GZI. Right. And then it's the exact same thing, but for the other side. So ME plus HE plus V2 squared over 2 plus GZE. All right. So this right here is the equation for this, this nozzle and diffuser. However, what these things usually break down to is because we always say it's steady state. And remember, when we say it's steady state, that means that there is no change of mass with respect to time. So how it breaks down to is the following. You then have the following. You would have Q minus W is equal to M, just M, times, then you start to show you put them together essentially. So it is now the following. It is HI minus HE plus V1 squared minus V2 squared. And this is all over 2, so it's going to be hard for me to show that, but I think you guys hopefully get the point. Plus G times the difference in Z, Zi minus Z, right? It ends up being this. So remember, so essentially because we only have one mass for it, we can combine these, right? They can now be fully combined. And so that is what you're going to see most of. You're going to see this right here. Now obviously HE and HI are going to refer to states 1 and 2, right? Like we're going to put H1 minus H2 plus V1 squared minus V2 squared over 2. G, and this will be Z1 and Z2. So this is how the questions will probably look when you get a hold of them, except on some question. There's the first question on your homework is going to have a turbine with, I think, one inlet here, another one here, and then one going out. So then you're going to have to obviously sum the two. But whenever it says like a nozzle, a diffuser, or a compressor with one inlet, one outlet, this is the equation you're going to end up using. So this is where I want to go from here, though. So in a nozzle, this is basically where we need to go from here. So in a nozzle, do you think that there's work being done? Anyone? Is there what does a nozzle do? Like when you put it on your hose, do you think it's creating any work? Wait for Tanner to say something.
Wouldn't it, because you're increasing the velocity at the other end, depending on, say, for a nozzle. So if it's the same mass in and the same mass out per time unit, wouldn't you have to be adding energy to the system? Or increasing the energy of...
You're right. There is an energy increase in the system. So, but remember, the work of the fluid is housed in these two right here, right? So let me rephrase. Is there any work like a shaft or any work like a something exterior, right? Are we spinning a turbine shaft in a nozzle? Are we lifting a weight? Are we X, Y, and Z, right? Anything like that. Is this happening in a nozzle?
No.
The answer is no. And so, what you can end up doing is that you can end up starting to get rid of some of these things. And this is specific to each one, which is important that you know what you're working on and you know what they do. So, and Tanner, you were correct, is that there is pressure changing. But remember, what is H is U plus PV. So the pressure changing is being accounted for in the energy of the flow work. Remember, flow work is being accounted for. But this external work is not existent. It does not exist in this. So, now let's go back. Let me kind of aim around this. All right. Didn't really think that far ahead. So now we have to go back here. All right. And like that. Okay. So now we can get rid of this. Is there any heat transfer? Like big heat transfer leaving the system? Does anybody want to gather that one? So for a lot of these questions, right, you have to look at it two ways. The first way is the heat transfer large enough to where it isn't like negligible, right? Like is it large enough, do you think, in a nozzle to make this like to make it really important that we calculate it?
I don't think the heat transfer would be significant.
I don't think so either. And so, usually heat transfer goes away too, because they'll either say like an insulated nozzle or heat transfer is negligible or something, right? So it usually goes away as well. But because what are the significant things in a nozzle? And also, what else goes away? There's one more thing in here. I forgot the bracket at the end here, or parenthesis at the end.
You're not changing height all that much, so you can probably get rid of Z.
Correct. So potential energy goes away because this would be a really weird looking nozzle if it went up, say like 50, let's say like 50 meters, and then came out. It'd be a weird looking nozzle, and it probably wouldn't work very effectively. So nozzles generally do not change any sort of significant height, right? So that goes away as well. The important thing in a nozzle is this right here. Honestly, even this part right here isn't very much. The flow work in a nozzle isn't very much. It's this part that is the huge part of a nozzle. It is the difference between velocity in and velocity out. And like I said, this is how a jet engine flies, is based on this right here alone. It is this right here. And so, this right here is the important part of the thing, and that's why it stays. So the nozzle equation generally reduces to that. It reduces to just these right here. So I'll go ahead and write that, just so everyone is aware. So M times H1. I'll just write H1 minus H2, just to talk about state points, I guess. V2, or V1 squared plus V2 squared. And I'm going to spread this out a little more. Over 2. And like I said, this generally is how it ends up looking. And so what ends up happening is you have to end up finding things from inside of this equation. So like it'll be like, here is the temperature at the exit of the nozzle. Here's the temperature at the inlet of the nozzle. The inlet velocity is this. Find the exit velocity, right? Things like that, right? And so this is a very simple manipulation once you figure out how to move things around. Pretty straightforward. And this right here is the exact same thing, except for a diffuser, it's inverted. So V2 and V1 change positions, essentially. They end up being one goes before the other. So, and you'll know that because, let's put it this way, so this is where you have to know what the thing you're working in. So let's say I give you velocity 1 and give you a way to find H1 and H2. If you find velocity 2 and it's lower than velocity 1 for a nozzle, it means that your equation is set up wrong, because a nozzle is supposed to be you're supposed to come out way faster than you went in. So that means you did the diffuser equation. So this is why it's important to know how things are working, once again, by positives and negatives. If you end up, let's say you have 100 here, and then at the exit of the nozzle you end up with like 20, that means that this is not a nozzle, it is a diffuser. And that's just simply because you messed up somewhere in here, right? So does everybody that makes sense? Essentially, there's a little mental check you have to do at the end and go, does this make sense? Does this nozzle actually increase the speed or not? And the same thing with these other ones over here. Compressors and pumps. Compressors, the temperature should go up after going into a compressor. For a turbine, the temperature should drop. That's another thing. Pressure should drop after a turbine, and for a compressor, pressure should go up. So they're the inverse of each other. Essentially, a compressor and a turbine are the inverse. So, for example, if you found H1 and H2, and I asked you for the work, right? And you found that the work of this compressor was a positive 100 kilowatts or something, that means that this is not a compressor, this is a turbine. And it's only because you flipped around some values and you got a positive value out. So if you know what you're working on, like I told you before, the sign doesn't matter as much as long as you know what you're working on. If you know that this is a compressor, it's very easy to go, well, it's a compressor, so it's minus 100 kilowatts instead, right? but it is important to make sure how you do this. So do be careful as to know what you're working on. But real fast, these things all sort of break down, and I'm going to go ahead and get a question going. Let's get all this out of the way. I'm going to do one real fast. We were a little bit ahead of the game. I think we did a little more than what we were supposed to last time. Oh, that's right. That's my other marker. Doop. All right. So let's see if I can find one of these questions really fast for us. And then there's heat exchangers, which is basically like the one we did last time. Let me see. Yeah. Yeah, we already did one like this. I don't really want to do that. So I'll do a, so let's see if this is a nozzle one. Let me see if I can find a nozzle. So 4.32 in the 8th edition. I will pull that up really fast. Give me a second. I have to go walk a long distance to grab my book. It's a live show, gentlemen. Alright. Apologies. This will be the reason why I don't get hired back. They're like, wait a minute, you had to get up during your lecture? By the way, if this is the only reason why I don't get hired back, I consider myself lucky. So, let's move in here. So, 4.32. It says, steam enters a well-insulated nozzle at 300 psi and 600 Fahrenheit. So, once again, guys, you start with what you know. So let's write that up here. So we have steam, so that's our fluid. It says enters a nozzle, so a well-insulated nozzle, so Q is 0, at a pressure 1 of 300 psi. All right? Then, one more thing, it says at a temperature, T1, of 600 Fahrenheit. So that's what they've given us. And then it says, and a velocity, V1, of 100 feet per second. And then it says, and exits at P2 of 40 psi. And it also says a velocity of 1,800 feet per second. So they have given us the exit velocity. 1,800 feet per second. That is quite a bit of difference. That means that this must be for a turbojet engine for sure. We got to go fast, guys. So that is what they've given us, and it says for steady state operation. So once again, that's another little piece of information they've given us. That means M1 is equal to M2. Essentially, there is no change in mass, right? So M1 is the only mass we have. It says for steady state operation and neglecting potential energy effects, so that's one more thing I have to add, but I'll just let you guys hold on to that. Determine the exit temperature in Fahrenheit. All right. So we need to find the exit temperature, so that is what we are looking at. So I will add a little text box for that. T2 is equal to that. So T2 is equal to something right now. The first thing that you should do for a question like this, and all questions like this, is you should initially write that long equation. That is the first thing you should do. Because for writing that long equation for this mechanism, it tells you what you have and what you need to find, right? So we can go ahead and write. So we have Q minus W is equal to M H1 minus H2 plus V. So this should be I think it should be, let me see, H1 minus H2. Yeah, okay, I think I've got it. I've got it right. Because then this will be a positive value. Okay, so then let's do v1 squared plus v2 squared. And I might flip this around, so that is subject to change. I do it from memory, of course. So, over 2. Ah, come on. Alright, so this is where we're at. So this is our equation for this, and like I said, we can get rid of some things right off the bat. So, Q, because it said well-insulated nozzle, and it's a nozzle, so there's no work, right? No exterior work. So what we're left with is this, right here. So I'm going to try and hurry this up and let you guys. So we are left with the following. We're left with M times H1 minus H2 plus V1 squared minus V2 squared over 2. Right? So this is what we are left with. And so in here, this is why I say write this first, is that our very first thing, well, they have given us what? They have given us exit velocity, inlet velocity, and they have given us temperature 1 and pressure 1. And since they have given us temperature 1 and pressure 1, we can find a way to find H1, right? So we will do that first. Let's find H1. So we don't actually know H1 yet. So I'll get that off. But we have a way to find it, right? So let's do that over here. So let's go through the book. We need to find, so we know P1 is equal to 300 psi. T1 is equal to 600. So I can already tell you that this is going to be definitely superheated, pretty sure. But we need to go and look anyway. So we shall. Let's go look at the tables, and we need to go to the English unit. So way, way down. Right here somewhere. So I always go to the pressure table when I have the chance. So we need to go to 300 psi, which is right here. 300 psi, and we are at a temperature of 600 degrees Fahrenheit. We are almost 200 degrees above that. So we are superheated right now. Right? Does everybody understand how I did that? Does that make sense? So, 300 psi, we are above this. So we need to go to the superheated tables. So let's go to 300 psi. 300 psi is right here. Now let's go to 600. So remember though, we need to grab enthalpy, not internal energy. So we need to know enthalpy is the third column over. So down here, slide across. Now you can grab whatever you think is useful here. If you want specific volume, if you want this, that's also fine. But I'm going to take enthalpy here, which is 1314.5. So, using the tables, we have found H1 is equal to 1314.5, and this is kilojoules per kilogram. Right? So, we now have that, which means I can go ahead and mark this off again as we have that. So, if we have all of these things, we now need to just know this last one. So, it makes sense that we could probably maneuver this equation to get that by itself, right? Does everybody agree with that? So, how we're going to do it? Well, you gotta multiply everything out, unfortunately. So, I'm gonna do M1, H1, minus M1, or M1, H2, plus M1 times V1 squared minus V2 squared, and then divided by 2. Right? So I've multiplied in the M through all of these things, and we're left with this. Then you move over H2 to the other side. So you are left with then the following. You are left with, then we can divide over M1. So we are left with the following. I think you would be left with H2 is equal to M1 H1 plus the difference of these two right here, which would be, although, let me see, you move this to the other side. Yeah, so the so the M goes away. So if you divide this over, if you divide the M1 over, you'll get rid of the M's on this side. So it should be H2 plus, or h1, sorry, h1 plus v1 squared plus v2 squared over 2. So that is where we are at right now. So really fast, there is a problem though. There's a slight issue. And the slight issue is that these units, these velocity units, are not in terms of what we want them to be. They are not in the right units, clearly. They are in feet per second, right? Does everybody understand that? So, that means we have to change things, right? Give me a second. So it means we have to change things, right? So by changing them, we have to mess with these units. And so how we have to do it is, remember, this right here is in BTUs per pound. This is in BTUs per pound. We need to change this to BTUs per pound. And how you do that is, the English units actually are really bad for this, and I'm sorry that I picked an English units question. But let me break open and find this one just to be sure that I get that right. It's 7. Oh no, yeah. So you divide by 1. Yeah, oh my god, this is terrible. I remember this now. So you have to change the units, and so how this one ends up being is that you have to turn this right here into foot pound, or you have to do foot pounds per second squared, and then 32.2 foot pounds per second squared is 1 BTU, and then 778 foot pound force is equal to 1 BTU. It's a really long one. I'll just write it out. But we are almost out of time. We might finish this next time. But essentially, you do this right across. You do H2 is equal to H1 plus these quantity in here. So V1 squared plus V2 squared divided by 2, as I said before. But then the last part here. So then it is, since we need to get feet squared per second squared, you have to use 1 pound force. So 1 pound force. So this is, by the way, this is the conversion. I'm going to write this over here. So 1 pound force is equal to 32.2 pound foot per second squared. So the second squareds cancel right there, which is good. And then you have to do 1 BTU. So BTU is equal to 778 foot pound force. So this is the conversion. Like I said, I'm sad to say that this is how it is. So this goes away. So let me actually, so real quick, we have feet squared per second squared, and we have to get that to BTUs per pound. So if you look at that, we get rid of 1 foot, we get rid of both the seconds, and then we are left with a pound. Then you get, by doing the next one, you add a BTU and you subtract off a foot pound force. You get rid of a pound force and you get rid of the last foot, which then leaves you with BTUs over pounds. I'm fairly certain. It's really hard to see that here, but this is how it ends up working. So, is everybody? I know that's quite a bit, and it'll make more sense when you actually see it. I promise you. But if I could write the units out in a little better, I would. But we don't have a whole lot of time. So this right here gets you where you need to go. That is a good point. They definitely wouldn't. So let me go ahead and just write everything out for you guys, and then you guys can see it. So real fast, I'll do it really quick. So it'd be H2 is equal to our H1 value, which was 1314.5 plus, let's go ahead and write out V1 squared. So V1 squared was 100 squared minus 1800 squared divided by 2. Right? And then we have to multiply, so I'll just do this. Actually, all you're doing is dividing here. Yeah, so it's times 1 over, so that's 1 over, and then down here is 32.2 times 778. So let me do that on a calculator really quick. I'll see if I can actually manage it. So let's do 100 squared times 1800 squared is that. Oh, no. Oh, no. That's not what we want. 100 squared minus, 1800 squared. Oh, wait, did I do that? Okay. Why is it saying square root, though? Did I hit a square root? Or am I just, like, tripping here? Yeah, okay, this has to be right. I'm going to bring a real calculator next time, sorry. So we have that. Then divide by 2. Then divided by 32.2. Then divide by 778. That seems really odd. I don't know if that ended up right. That doesn't seem right to me. So let's try that again. 100 squared minus 1800 squared. It shouldn't be positive though, but okay. There it is. Sorry, I'm 2 divided by 32.2 divided by 778. Okay, I guess it was right. Sorry. I just, for some reason, that didn't look right to me. Nope. 1314.5. So, you get a enthalpy value at the end of this, it looks like. So, 1250 at the end. 1250. And so you can go look up 1250 enthalpy at the pressure of 40 psi, which I will do really quick just to like show you, but I'm pretty sure this is what we got to do here. So let's go look at this. So back in here, so it was at what psi did I say? 40. So 40 psi here. So we are still superheated because this is the enthalpy of saturated vapor. So we are still superheated, but not by much. So we actually came down in energy, which makes sense. This is how it should have happened. And so if we now go to the superheated tables, which I will do that now, we have to go to 40 psi. Sorry for how long this is taking. You go to 40 psi and you find our enthalpy here. And so our enthalpy was 1250. So it has been between 400 and 500. And it looks like it's fairly close to the right in between. So we could say 450 is our temperature, something like that, at 40 psi. So we're in here. I'm going to see if that's the right answer, although this is the 6th edition, so I actually don't have the 6th edition in front of me. Yeah, here it is. I found it. I'll see if that ends up right. I'm pretty sure it will, though. Unless I made a weird calculator error. So... yeah, apologies for this. It's taken too long. Because I don't have the 6th edition solutions on this computer for some reason. Alright, let's see. See what we got here. 1250.03, 428 they say. So our number was 1250.03, and they say 428 in the tables. Did I just read that wrong? Oh, yeah. Okay. I guess I did read it wrong. So that right there, they interpolated in between these values. So it was closer to this one than it is the other one. So that's what they got. They said that they got that. So 428 is what they say the answer is. So, once again, sorry that took so long. But this is the type of question. There is a question on your homework just like this. It is a nozzle, and then you also have a diffuser, and you have a turbine with multiple inlets and outlets. And also, the last question is a change of height. It has a potential energy effect, so you guys have to work on that. And the homework has been uploaded today. I apologize for not doing it earlier. So I've given you until next Wednesday to do it. You have a full week from today. So you guys are free to go. Hopefully this made some sort of sense.